So here's something to think about as you settle in tonight. Right now, somewhere in the deep Atlantic, maybe 1,000 feet below the surface, there's a submarine gliding through water so dark that if you turned off every light inside, you wouldn't be able to see your own hand in front of your face. The crew might be eating dinner. Someone's probably reading a paperback in their bunk. The reactor is humming along, splitting atoms to turn a shaft that pushes the whole vessel forward at a speed that's still classified. And the ocean above them, 1,000 feet of cold, heavy, crushing ocean, has absolutely no idea they're there. Nobody does. That's the whole point. Submarines are, when you really sit with it, one of the most audacious things human beings have ever built. We are land animals. We breathe air. We're not even particularly good swimmers compared to most marine creatures. And yet, we figured out how to seal ourselves inside a metal tube, sink it beneath the waves on purpose, keep everyone alive and breathing for months at a time, and move through the deep ocean like it's just another highway. That's wild. And the story of how we got there, from the very first clumsy attempts to the nuclear-powered leviathans cruising the ocean floor today, is one of the best engineering stories ever told. So let's talk about it, all of it. How submarines actually work, from the physics of why they sink and float, to the nuclear reactors that power them, to the sonar systems that let them see without light, to the life support that keeps 130 people breathing recycled air for 90 days straight. We'll get to all of it. But let's start where it makes sense to start, which is with a question that seems almost stupidly simple until you really think about it. How do you make something sink? Okay, that sounds obvious. You throw a rock in a pond, it sinks. Done. But a submarine isn't a rock. A submarine is a vessel. It has air inside, it has people inside, it has machinery and weapons and a kitchen and bunks. It's a big hollow thing, and big hollow things tend to float. That's why ships float. A steel ship can weigh tens of thousands of tons and still sit right there on the surface, because the hull displaces enough water that the buoyant force pushing up equals the weight of the ship pushing down. Archimedes figured this out around 250 BC, and it's still the whole game. The principle is simple. Any object submerged in a fluid experiences an upward force equal to the weight of the fluid it displaces. If the object weighs less than the water it pushes aside, it floats. If it weighs more, it sinks. So a submarine, at its most fundamental level, is a vessel that can change how much it weighs relative to the water it displaces. And the way it does this, the way every submarine that has ever worked does this, is by letting water in and pushing water out. That's it. That's the core trick. A submarine has ballast tanks, which are essentially large compartments built into the hull that can be filled with either air or seawater. When the tanks are full of air, the submarine is lighter overall, and it floats on the surface like any other ship. When the crew wants to dive, they open valves at the bottom of the ballast tanks and vents at the top, and seawater rushes in while air escapes out. The submarine gets heavier. It starts to sink. When they want to come back up, they blow compressed air into the tanks, which forces the water back out through those bottom valves, and the submarine gets lighter again. It rises. Think about what that means in practice. You're essentially building a ship that can make itself heavier or lighter on command. And the engineering challenge isn't just making that work, it's making it work precisely, controllably, and safely, hundreds of feet below the surface, where the water pressure is trying very hard to crush your vessel into scrap metal. But we'll get to the pressure problem. For now, just hold on to that image. Ballast tanks, air in, water out. water in, air out. That's the beating heart of every submarine ever built. Now, people have been dreaming about going underwater for a very, very long time. Alexander the Great supposedly descended into the sea in a glass barrel around 332 BC. That's almost certainly legend, but the fact that the story existed tells you something about how long humans have been fascinated by the idea. Leonardo da Vinci sketched designs for an underwater vessel in the late 1400s, though he famously refused to publish the details because, as he wrote, he feared the evil nature of men who would use it to practice assassinations at the bottom of the sea. Which, honestly, was a pretty accurate prediction of what submarines would eventually be used for. But Leonardo's sketches were just sketches. Nobody built them. The first person who actually built something that went underwater and came back up, at least the first person we have a credible record of, was a Dutch inventor named Cornelis Drebbel, and his story is genuinely fascinating. Drebbel was born in 1572 in Alkmaar, in the Netherlands, and he was one of those restless, polymathic minds that the Renaissance seemed to produce in batches. He was an engraver, an inventor, a lens maker, a dyer. He developed a famous scarlet dye that was used for decades after his death. He built a perpetual motion machine that was almost certainly powered by changes in atmospheric pressure and temperature, which is clever, even if it wasn't actually perpetual. He ended up in the court of King James I of England, where he was essentially the court inventor, building gadgets and curiosities for the royal entertainment. And sometime around 1620, Drebbel built a submarine, or rather, he built what we'd probably call a submersible, a vessel that could travel underwater for a limited time. The details are frustratingly sketchy because Drebbel himself didn't leave detailed technical records, and most of what we know comes from second-hand accounts written years later. But here's what we can piece together. It was essentially a wooden rowboat enclosed with a waterproofed leather covering, sealed with tallow, rendered animal fat, to keep the water out. It had oars that poked through the hull via sealed leather sleeves, so rowers inside could propel the vessel while it was submerged. And according to multiple contemporary accounts, Drebbel demonstrated this vessel on the River Thames, traveling underwater from Westminster to Greenwich, a distance of about 5 miles, at a depth of roughly 12 to 15 feet below the surface. Now, 12 to 15 feet doesn't sound like much, and it wasn't, compared to what would come later. But think about what Drebbel actually accomplished. He sealed human beings inside a vessel, submerged it in a river, kept them alive and breathing for several hours, and brought them back to the surface. In 1620, that's 20 years before the English Civil War. Shakespeare had been dead for only 4 years, and here's this Dutch inventor cruising beneath the Thames in a leather-covered rowboat. King James himself reportedly witnessed a demonstration, though there's no record of him volunteering to go aboard. Here's the thing that's really interesting about Drebbel, though. Some accounts suggest he had a way of refreshing the air inside the vessel. One source, written decades later by the chemist Robert Boyle, yes, that Robert Boyle, of Boyle's Law, claimed that Drebbel had developed a chemical substance that could restore the air and make it breathable again. Boyle wrote that Drebbel had a liquor that he could release inside the submarine to revive stale air. Now, what was this substance? Nobody knows for certain. Some historians have speculated it was heated saltpeter, potassium nitrate, which, when heated, releases oxygen. If that's true, and it's a big if, Then Drebel was generating oxygen to sustain his crew more than 150 years before oxygen was even formally identified as an element by Antoine Lavoisier in the 1770s. He wouldn't have understood what he was doing in chemical terms. He wouldn't have known about oxygen as a gas. But he might have figured out, through trial and error, that heating this particular substance made the air inside a sealed space breathable again. That's the kind of practical, empirical engineering that has driven so much of human progress. People figuring out that something works long before they understand why it works. But Drebel's submarine, clever as it was, didn't really go anywhere in terms of development. It remained a curiosity, a demonstration piece. Nobody built a fleet of leather-covered rowboat submarines. The technology wasn't ready. The materials weren't ready. And crucially, nobody had figured out a compelling reason to go through all the trouble. That would change. And the reason, as Drebel's contemporary Leonardo had predicted, would be war. Let's jump forward about 150 years to the American Revolution, because this is where submarines stop being curiosities and start being weapons. The year is 1775. The British Navy is the most powerful maritime force in the world, and it's blockading American harbors, choking off supplies to the rebellious colonies. The Americans have almost no navy to speak of. They can't fight the British at sea in any conventional sense. And so a young Yale graduate named David Bushnell starts thinking about unconventional approaches. Bushnell was from a farm in Saybrook, Connecticut. He didn't come from money or privilege. He actually didn't enroll at Yale until he was 31, after his father died, and left him a small inheritance. But he was brilliant, and he was obsessed with explosives. As a student, he demonstrated that gunpowder could be detonated underwater, which was something many people at the time didn't believe was possible. And from that insight, he built the Turtle. The Turtle, and yes, that was its actual name, was a one-man submarine designed to sneak up on British warships, attach an explosive charge to their hull, and slip away before the charge detonated. It was shaped roughly like a large egg, or maybe two turtle shells pressed together, which is where the name came from. It was about 6 feet tall and about 3 feet wide, built from oak staves bound with iron hoops, like a barrel. The operator sat inside on a small seat, working a hand-cranked propeller to move forward, a second hand crank to move vertically, and foot-operated pedals to control a rudder. There was a small conning tower at the top with tiny glass windows for visibility at the surface. To dive, the operator opened a valve to let water into a small ballast tank at the bottom. To surface, he worked a hand pump to push the water back out. The air supply was whatever was sealed inside the hull when the hatch closed, enough for about 30 minutes of operation. Think about that for a second. One person, alone, inside a dark wooden egg, hand-cranking themselves through a harbor full of enemy warships, with 30 minutes of air and an explosive charge strapped to the outside. The courage that took is almost incomprehensible. On the night of September 6th, 1776, the Turtle made its famous attack run against the HMS Eagle, a 64-gun British flagship anchored in New York Harbor. The operator was Sergeant Ezra Lee. Bushnell himself was too ill to make the attempt. Lee cranked the Turtle out into the harbor under cover of darkness, submerged, and maneuvered beneath the Eagle's hull. The plan was to use a drill mounted on top of the Turtle to bore into the ship's wooden hull, screw in an iron bolt, and attach the explosive charge to the bolt with a rope. Then Lee would crank away, and a timing mechanism would detonate the charge after he was clear. It didn't work. Lee couldn't get the drill to penetrate the hull. The most common explanation is that he hit a spot where the hull was reinforced with copper sheathing or iron fittings, and the hand-powered drill just couldn't get through. After several attempts, with his air running low and dawn approaching, Lee had to abort. He released the explosive charge, which drifted away and eventually detonated harmlessly in the East River, and he cranked the turtle back to safety. So the turtle failed in its mission. The British ships were not sunk. But here's what matters about the turtle, and why Bushnell's name belongs in the story of submarine engineering. He proved the concept. He demonstrated that a vessel could submerge, navigate underwater, approach an enemy ship undetected, and return. The execution wasn't there yet. The materials, the propulsion, the air supply, all of it was too primitive. But the idea was sound, and the idea would not go away. What happened over the next century is a slow, sometimes painful process of people trying to solve the problems Bushnell had run into. How do you propel a submarine faster and farther than a man can crank? How do you give the crew enough air to stay submerged for more than 30 minutes? How do you navigate underwater when you can't see where you're going? How do you build a hull strong enough to withstand the pressure at depth? Each of these problems would take decades to solve, and each solution would create new problems of its own. And the people who worked on these problems, some of them geniuses, some of them dreamers, some of them con men, and a few who were all three at once, their stories are some of the most fascinating in all of engineering history. Let's start with a man named Robert Fulton, because you probably know his name already, and you probably know it for the wrong reason. Most people, if they remember Robert Fulton at all, remember him as the steamboat guy. And that's fair. He did build the Clermont, the first commercially successful steamboat, which chugged up the Hudson River in 1807 and changed river transportation forever. But before Fulton was a steamboat man, he was a submarine man. And his submarine story is one of those tales that involves war, espionage, rejected genius, and two rival empires bidding for the same weapon. Fulton was an American, born in Pennsylvania in 1765, but he spent a big chunk of his career in Europe. He was a painter first, actually, went to London to study art, wasn't particularly successful at it, and gradually drifted toward engineering and invention. By the late 1790s, he was living in Paris, and he had become obsessed with an idea, a submarine that could destroy the British Navy. Now, you have to understand the context. This is revolutionary France. Napoleon is rising to power. France and Britain are locked in a struggle that will define European politics for the next 2 decades. And Britain's greatest advantage is its navy. The Royal Navy is the most powerful fleet in the world, and France simply cannot match it ship for ship. Fulton saw this and thought, what if you didn't have to match it ship for ship? What if a small, cheap, underwater vessel could sneak up to a massive warship and destroy it? You wouldn't need a fleet. You'd need a handful of submarines and some explosives, and suddenly, Britannia doesn't rule the waves anymore. He called his submarine the Nautilus. Yes, the same name Jules Verne would later borrow for Captain Nemo's fictional submarine, and that's not a coincidence. Verne was directly inspired by Fulton's story. The Nautilus was built in 1800, and it was a genuine leap forward from Bushnell's Turtle. Where the Turtle was a one-man barrel, the Nautilus was a proper vessel, about 21 feet long, with a copper hull over iron ribs. It carried a crew of 3, later 4. And here's what's really important about the Nautilus from an engineering standpoint. Fulton thought carefully about the dual nature of submarine operation. See, a submarine has to do 2 very different things. It has to travel on the surface, sometimes for long distances, to get where it's going. And then it has to submerge and operate underwater. These are almost opposite engineering challenges. On the surface, you want speed and efficiency and fresh air. Underwater, you want stealth and the ability to maneuver in 3 dimensions. Fulton addressed this by giving the Nautilus a collapsible mast and sail for surface travel. When the boat needed to dive, the crew would fold down the mast, seal the hatches, and switch to hand-cranked propulsion, a propeller turned by the crew. It's a simple idea, but it's the first real attempt to design a submarine that could handle both regimes of operation, surface and submerged, with different systems for each. Fulton demonstrated the Nautilus in the Seine River and then in the harbor at Brest on the French Atlantic coast. He successfully submerged, maneuvered, and even destroyed a target vessel with a towed explosive charge, basically a mine on a line that the submarine would drag beneath an enemy ship. The French Naval Commission watched the demonstrations and was unimpressed. Or rather, they were impressed by the technology, but horrified by the implications. French admirals, much like admirals everywhere, did not like the idea of a weapon that could make their own surface ships obsolete. There's a recurring theme in submarine history, and it's this. The people who controlled existing navies almost always resisted submarines, because submarines threatened to upend the entire power structure. If a cheap little underwater boat could sink a magnificent ship of the line, then what was the point of building magnificent ships of the line? And if you were an admiral who had spent your entire career commanding magnificent ships of the line, that was not a question you wanted anyone asking. So Napoleon's navy said no. Fulton, frustrated, did what any self-respecting inventor mercenary would do. He went to the other side. He crossed the English Channel and offered his submarine technology to the British. The British were interested, cautiously, because they could see the defensive potential. If France built submarines, Britain needed to understand them. Fulton did some demonstrations in British waters, successfully blew up a brig called the Dorothea, using his towed mines in 1805, and for a brief moment it seemed like the Royal Navy might actually fund a submarine program. But then, Trafalgar happened. Nelson destroyed the combined French and Spanish fleet in October 1805, and suddenly, Britain's naval supremacy was so overwhelming that they didn't need submarines. Why fund a weapon that might eventually be used against you when you've already won? Fulton went home to America, pivoted to steamboats, and made his fortune there. But his submarine work mattered enormously. He'd proven that a purpose-built submarine could operate in open water, not just rivers and harbors. He'd pioneered the concept of dual surface and submerged propulsion systems, and he'd demonstrated that submarine-delivered explosives could actually sink real ships. The engineering was getting closer. The politics just weren't ready. Now let's skip ahead a few decades, because the next really important chapter in submarine history happens during the American Civil War, and it's one of the most dramatic and heartbreaking stories in all of engineering. The H.L. Hunley. If you know one submarine from the 19th century, it's probably this one, and for good reason. The Hunley was built by the Confederacy in 1863 during the Civil War, and it became the first submarine in history to sink an enemy warship in combat. But the cost of that achievement was staggering. The story starts with Horace Lawson Hunley, a wealthy lawyer and plantation owner from Tennessee who had relocated to New Orleans. Hunley was a Confederate patriot who believed, much like Fulton had believed about France, that the South could neutralize the North's overwhelming naval superiority with submarine warfare. The Union Navy was blockading southern ports, strangling the Confederacy's ability to trade and resupply. If submarines could break that blockade, even partially, it might change the course of the war. Hunley helped fund and develop a series of submarine prototypes in New Orleans and Mobile, Alabama. The first attempts were crude, converted steam boilers basically, sealed up and fitted with propellers. They didn't work well. But the engineers kept iterating, and by 1863, they had produced a vessel that was genuinely innovative. The H.L. Hunley was about 40 feet long, built from iron plates riveted together, with a roughly circular cross-section. Imagine a long iron tube, tapered at both ends. It carried a crew of 8 men plus a commander. And here's the thing about propulsion. It was still muscle power. 8 men sat on a bench inside this iron tube, shoulder to shoulder, and they turned a hand crank connected to the propeller shaft. The commander sat at the front, operating the rudder and a pair of diving planes, small fins that angled the boat up or down to control depth. Think about what that was like for a moment. You're inside an iron cylinder barely 4 feet in diameter. It's dark. There's a single candle for light, and when the candle goes out, that's also your warning that the air is getting too thin to breathe. You're cranking a handle as hard as you can, in rhythm with 7 other men, and the whole vessel is moving through black water at maybe 2.5, 3 knots. You can't see anything. The commander is navigating by compass and by occasionally peering through tiny glass viewports in the conning towers, which are barely raised bumps on the top of the hull, and everyone aboard knows, that this machine has already killed people, because the Hunley's testing history was catastrophic. During a training exercise in Charleston Harbor on August 29, 1863, the submarine swamped and sank when someone accidentally stepped on the lever controlling the diving planes while the hatches were still open. 5 of the 9 crew members drowned. The boat was raised, refitted, and put back into service. Then, on October 15, 1863, during another training dive, the Hunley sank again. This time, all 8 crew members and Horace Hunley himself, who had taken personal command to restore confidence in the vessel, were killed. When the submarine was recovered from the harbor floor, the crew was found still at their stations, the hand crank still in their grip. The candle had been extinguished. They had suffocated in the dark, unable to surface. 13 men dead, and the submarine hadn't even gone into combat yet. Any reasonable military would have scrapped the project. But the Confederacy was desperate, and the blockade was tightening, and so the Hunley was raised again, refitted again, and a new volunteer crew was found. Think about the courage, or desperation, it took to climb into that iron coffin after what had happened. On the night of February 17, 1864, the Hunley set out from Sullivan's Island in Charleston Harbor, heading for the USS Housatonic, a 12-gun Union sloop of war that was part of the blockading squadron. The Hunley was armed with a spar torpedo, essentially a copper cylinder packed with about 135 pounds of black powder, mounted on a long iron pole that jutted forward from the bow. The plan was simple and terrifying. Ram the spar into the enemy ship's hull, back away, and then trigger the explosive by pulling a rope attached to the detonator. The Hunley reached the Housatonic. Lookouts on the Union ship spotted something in the water at the last moment, but it was too late. The spar torpedo struck the Housatonic's starboard side near the stern, and the charge detonated. The explosion tore a massive hole in the hull, and the Housatonic sank in about 5 minutes with the loss of 5 Union sailors. The Hunley had done it. First submarine in history to sink an enemy warship. But the Hunley never came home. The submarine disappeared that night, and for over a century, nobody knew exactly what happened. It wasn't until 1995 that the wreck was located on the ocean floor, about 1,000 feet from where the Housatonic went down. When the Hunley was finally raised in 2000, the crew was found at their stations, just like the previous crew. There was no sign of panic, no sign they had tried to escape. The most likely explanation, based on years of forensic analysis, is that the concussive force of their own torpedo blast killed or incapacitated the crew. They were simply too close to the explosion. The shock wave traveled through the water and through the iron hull and through their bodies with devastating force. You know, we think of explosions as fire and shrapnel, but underwater, the physics are different. Water doesn't compress the way air does. When a charge goes off in open air, the blast wave dissipates relatively quickly because the air molecules can spread apart, absorb some of that energy. But water is nearly incompressible, so the pressure wave from an underwater explosion travels faster, farther, and hits harder. That 135 pounds of black powder going off just a few feet from the Hunley's thin iron hull would have sent a pressure spike straight through the metal and into the bodies of those 8 men cranking their propeller shaft. The leading theory is that the blast caused lethal pulmonary trauma. Essentially, the shock wave ruptured their lungs and possibly other soft tissue organs, without leaving much visible external injury, which is why they were found sitting at their posts, hands still near the crank. They may have been dead within seconds, before they even understood what had happened. And that's the tragedy of the Hunley in a nutshell. 31 men died across its 3 crews, 13 before it ever accomplished its mission, and then the final 8 on the very night it succeeded. The first submarine to sink an enemy warship, and it killed more of its own sailors than it killed of the enemy's. That ratio, that brutal math, would haunt submarine development for decades. But here's the thing. The Hunley proved something that couldn't be unproven. It showed that a submarine, even a crude, hand-cranked, barely functional one, could sink a major warship. And that changed the strategic calculation for every navy in the world. Not immediately, not overnight, but the idea was now loose. You couldn't put it back in the box. Admirals might not like submarines. They might consider them ungentlemanly or impractical, but they could no longer pretend they were impossible. So, what happened next? Well, for a while, not much. The American Civil War ended in 1865, and the urgency that had driven the Confederacy to experiment with desperate weapons evaporated. The major navies of the world, Britain, France, the United States, went back to building bigger and better surface warships. This was the age of the ironclad, the beginning of the battleship era. Massive steel ships with turret-mounted guns, steam-powered, armored. That's where the money and the prestige were. Submarines were still seen as oddities, weapons of the weak, something a lesser power might resort to, but that a proper navy wouldn't need. And honestly, the technology wasn't there yet. The Hunley had laid bare the 2 fundamental problems that had plagued every submarine since Drebel's leather boat on the Thames: propulsion and air. You need a way to move underwater that doesn't depend on human muscle, and you need a way to breathe, or at least a way to carry enough air to stay down for useful periods of time. Hand cranking was exhausting and slow. The Hunley could barely make 4 knots, and the crew was spent after a short distance. That's not a practical weapon. That's a suicide mission with a crank handle. So the question became, what moves a submarine? And this is where the story gets really interesting, because the answer didn't come from one breakthrough. It came from a slow, messy convergence of several different technologies, and it involved one of the most fascinating rivalries in engineering history. Let's talk about John Philip Holland, born in 1841 in Liscannor, a small town on the west coast of Ireland. His father was a coast guard, and young John grew up watching the sea, which probably shaped his imagination in ways he couldn't have predicted. He became a school teacher, taught science and mathematics, but what consumed his private hours was submarines. Holland was an Irish nationalist at a time when Ireland was under British rule, and he saw the submarine as the great equalizer, a weapon that could allow a small, poor nation to challenge the mightiest navy on Earth. Sound familiar? It's the same logic that drove Bushnell during the Revolution, the same logic that drove the Confederacy. Submarines keep attracting people who are outmatched on the surface. Holland emigrated to the United States in 1873 and almost immediately began designing submarines. His early designs were funded, remarkably, by the Fenian Brotherhood, an Irish-American organization dedicated to Irish independence from Britain. They actually paid for his first 2 prototypes, which became known as the Fenian Ram. Think about that for a second. A secret Irish revolutionary organization funding submarine development in New Jersey in the 1880s. History is stranger than fiction. The Fenian Ram, launched in 1881, was a genuine leap forward. It was about 31 feet long, powered by a 15-horsepower Brayton petroleum engine on the surface, and it could dive to about 60 feet. Holland understood something crucial that many of his competitors didn't. A submarine shouldn't just sink straight down and float straight up like a cork in a bathtub. It should dive dynamically, using angled fins, what we'd call hydroplanes, to control its angle of descent and ascent, the same way an airplane uses its control surfaces to climb and descend. This was a fundamental insight. Instead of relying purely on adjusting ballast to be perfectly neutrally buoyant at every depth, which is incredibly difficult to do precisely, you could use forward motion combined with angled diving planes to push the boat down or pull it up. It's the difference between trying to hover a helicopter at exactly the right altitude versus flying an airplane that naturally maintains altitude through its forward speed and wing angle. Much more controllable, much more stable. But Holland still had the propulsion problem. His petroleum engine worked fine on the surface, where it could draw in air for combustion and vent exhaust. But underwater? You can't run a combustion engine underwater. It needs oxygen, and it produces carbon monoxide and carbon dioxide. You'd suffocate your crew in minutes. So Holland, like everyone else, was stuck with the same dilemma. One type of power for the surface, another type for submerged travel. Now, right around this same time, halfway across the Atlantic, another engineer was wrestling with the exact same problem. Simon Lake, born in 1866 in Pleasantville, New Jersey, so not far from Holland actually, had read Jules Verne's 20,000 Leagues Under, the sea as a boy, and become obsessed with submarines. Lake's approach was different from Holland's in some fascinating ways. Where Holland designed boats meant for warfare, Lake initially envisioned submarines for peaceful purposes, salvage, exploration, undersea mining. And where Holland favored dynamic diving with hydroplanes, Lake preferred to keep his boats level and control depth purely through ballast. Lake even designed submarines with wheels on the bottom so they could roll along the ocean floor, which is a wonderfully eccentric idea. The rivalry between Holland and Lake would define American submarine development for decades, and it got personal. Both men competed fiercely for U.S. Navy contracts. Both believed the other's approach was fundamentally wrong, and both had enough ego to fill a ballast tank. But here's what matters for our story. Both of them converged on the same solution to the propulsion problem, because by the 1890s, a technology had matured just enough to make it viable: the electric battery. Now, batteries had existed in various forms since Alessandro Volta's pile in 1800, but they were heavy, weak, unreliable, and short-lived. Not exactly what you want powering a vessel underwater. But by the late 19th century, lead-acid batteries, the same basic chemistry that starts your car today, had improved dramatically. They were rechargeable. They could deliver reasonable amounts of power, and critically, they produced no exhaust. An electric motor running on battery power needs no air and produces no fumes. It's quiet, it's clean, and it works perfectly well in a sealed hull underwater. The catch, of course, is that batteries run out. And when they do, you need to recharge them, which requires a generator, which requires an engine, which requires air. So the elegant solution, the one that would become the standard for submarines for the next 60 years, was the dual propulsion system. You carry a combustion engine and an electric motor. On the surface, you run the combustion engine, which both propels the boat and drives a generator to charge your batteries. When you dive, you switch to electric motors running on those stored batteries. When the batteries get low, you surface, fire up the engine, recharge, and dive again. It sounds simple when you say it like that, but making it work in practice was enormously difficult. You're cramming two complete propulsion systems into a hull that's already desperately short on space. You've got a diesel or gasoline engine with all its fuel, cooling, and exhaust systems, plus banks of lead-acid batteries that are incredibly heavy. We're talking tons and tons of batteries, plus electric motors, plus generators, plus all the switchgear and controls to manage the transition between the two systems. And all of this has to fit inside a pressure hull that's small enough to be practical and strong enough to withstand the crushing force of the ocean at depth. Holland figured this out first, or at least he got a working version to the Navy first. His sixth submarine design, the Holland 6, launched in 1897, was the one that finally convinced the U.S. Navy. It was about 53 feet long, displaced about 75 tons submerged, and it had exactly this dual propulsion arrangement: a 45 horsepower gasoline engine for surface running and battery charging, and an electric motor for submerged operations. It could make about 8 knots on the surface and 5 knots submerged, and it could dive to about 75 feet. It also carried a single torpedo tube and a pneumatic gun. It was a warship, no question about it. On April 11, 1900, the U.S. Navy purchased the Holland 6, and it was commissioned as USS Holland, SS-1, the first officially commissioned submarine in the United States Navy. Holland was 60 years old. He'd been working on submarines for nearly 3 decades. And here's where the story takes a turn that's both predictable and heartbreaking, because Holland didn't get to enjoy his triumph for long. The company he'd founded, the Holland Torpedo Boat Company, had been taken over by a businessman named Isaac Rice, who merged it into a new corporation called the Electric Boat Company. Holland found himself increasingly sidelined in his own company, his designs modified without his approval, his name used to sell boats he didn't fully endorse. He resigned in 1904, bitter and frustrated, and spent his remaining years trying to develop new submarine designs independently. He died in 1914, just as the weapon he'd spent his life perfecting was about to reshape the entire nature of naval warfare in ways even he might not have imagined. But we're getting ahead of ourselves. Because before we get to the First World War, there's something we need to talk about. Something that might seem like a small engineering detail, but that turns out to be one of the most important decisions in the entire history of submarine design. And it has to do with what kind of fuel you burn in that surface engine. Holland used gasoline in the Holland 6, and gasoline engines were common in early submarines built by several navies in the first decade of the 20th century. But gasoline has a problem. Actually, gasoline has several problems, but one of them is really, really dangerous on a submarine. Gasoline vapor is heavier than air, and it's explosive at relatively low concentrations. Somewhere between about 1 and 8% mixed with air is all it takes. Now, on a surface ship, that's manageable. You've got open decks, wind, natural ventilation carrying fumes away. But inside a submarine, you've got a sealed metal tube with limited ventilation, warm machinery, and fuel tanks that are never perfectly sealed. Gasoline vapor seeps out. It pools in the bilges, in the low spots of the hull, in the corners where air doesn't circulate well. And all it takes is one spark, from an electrical switch, from a motor brush, from metal scraping against metal, and you've got an explosion inside a pressurized steel cylinder with nowhere for the blast to go except through the crew. And this wasn't theoretical. Early gasoline-powered submarines had a terrible record of fires and explosions. The British A-class submarines, built in the early 1900s, ran on gasoline, and they were notorious for it. In 1905, 5 crew members aboard HMS A5 were killed when gasoline vapors ignited during an engine test. The French submarine Farfadet sank in 1905, the Luton in 1906. These early boats were dangerous in ways that went beyond the inherent risk of going underwater. The gasoline itself was trying to kill you before the ocean even got a chance. And there was another problem, maybe less dramatic, but just as serious for a military vessel. Gasoline engines produce exhaust that contains carbon monoxide, colorless, odorless, and lethal. In a submarine, where you're constantly recycling air, where the ventilation is marginal at best, carbon monoxide poisoning was a persistent, insidious threat. Crews reported headaches, nausea, dizziness, confusion, all symptoms of CO exposure. Some of them probably didn't even realize what was happening until they were too impaired to do anything about it. You're operating complex machinery, navigating underwater, managing weapons systems, and your brain is slowly being starved of oxygen. That's terrifying in a way that's different from an explosion. It's quiet and creeping. So the question became obvious pretty quickly. Is there something better than gasoline? And the answer was yes. Diesel fuel. Rudolf Diesel had patented his compression ignition engine back in 1893, and by the early 1900s, diesel engines were becoming practical for marine applications. Here's what made diesel so much better for submarines. First, diesel fuel has a much higher flash point than gasoline, somewhere around 52 to 96 degrees Celsius compared to gasoline's minus 43 degrees. That means diesel doesn't readily produce explosive vapors at normal temperatures. You could practically drop a lit match into a puddle of diesel fuel and it might just go out. Try that with gasoline, and you'll learn a very fast, very painful lesson about flash points. So right away, the explosion risk drops dramatically. Second, diesel engines are more fuel efficient than gasoline engines. They extract more energy per liter of fuel, which means more range for the same amount of fuel carried or less fuel needed for the same range. On a submarine, where every cubic foot of space matters, where you're trying to cram in torpedoes and batteries and crew quarters and ballast tanks and provisions, being able to carry less fuel for the same performance is a huge advantage. And third, and this is one of those details that sounds minor but really isn't, diesel exhaust, while certainly not pleasant, contains less carbon monoxide than gasoline exhaust. It's still not something you want to breathe, but the acute poisoning risk is lower. The French Navy, interestingly, was among the first to make the switch. The French submarine Aigrette, launched in 1904, is often cited as the first submarine to use a diesel engine. though there's some debate about whether it was truly the first or just among the earliest. The French had been aggressive submarine builders. They had one of the largest submarine fleets in the world at that point, and they understood the gasoline problem firsthand. The transition wasn't instant, though. Early marine diesel engines were heavy, unreliable, and difficult to manufacture to the tolerances needed. They vibrated terribly. They were loud. They were hard to start in cold conditions. But they didn't explode, and that turned out to be a pretty compelling argument. By around 1910, most major navies were either switching to diesel or actively planning to. The British, the Germans, the Americans, the Japanese. Everyone recognized that diesel-electric was the way forward. And when I say diesel-electric, I mean the same basic architecture that Holland and Lake had converged on, just with diesel replacing gasoline. Diesel engines on the surface, driving generators that charge lead-acid batteries, electric motors for underwater propulsion. That fundamental architecture, diesel-electric, would dominate submarine design for the next 50 years. Think about that. A basic engineering configuration worked out in the first decade of the 20th century remained the standard through 2 world wars and into the Cold War era. That's remarkably durable for a piece of military technology. Now, let's talk about what happened when that technology went to war, because the First World War is where submarines stopped being experimental curiosities and became one of the most devastating weapons in naval history. And the country that proved it wasn't Britain, wasn't France, wasn't the United States. It was Germany. The German Navy, the Kaiserliche Marine, came to submarines relatively late compared to the French or the British, but they came with purpose. By 1914, Germany had about 28 operational U-boats, which is what they called their Unterseeboots. That's not a huge number. Britain had more submarines. France had more submarines. But Germany had something the others didn't, a strategic reason to use them aggressively. Here's the thing about Germany's position in 1914. The Royal Navy was the most powerful surface fleet in the world. Britain had spent decades and enormous sums of money maintaining naval superiority. The German high seas fleet was formidable, but it was outnumbered. And after the Battle of Jutland in 1916, which was technically inconclusive, but strategically a British victory, because the German fleet never seriously challenged the Royal Navy again, Germany's surface ships were essentially bottled up in port. But Britain had a vulnerability, and it was a profound one. Britain is an island. It imports food. It imports raw materials. It imports everything it needs to feed its population and fuel its war effort. All of that comes by sea, on merchant ships, through shipping lanes that stretch across the Atlantic. And those shipping lanes, in 1914, were essentially unprotected against a threat that nobody had really planned for: submarines attacking commercial vessels. Remember what we talked about earlier, about submarines being the weapon of the weaker naval power? This is exactly that dynamic, playing out on the largest possible scale. Germany couldn't beat the Royal Navy in a surface engagement, but it didn't need to. It just needed to sink enough merchant ships to starve Britain into submission. And the U-boat was the perfect tool for that job. The early U-boat campaigns were tentative, constrained by international law and the so-called prize rules, conventions that required a warship to surface, identify a merchant vessel, give the crew time to abandon ship, and then either capture or sink it. These rules had been developed for surface raiders, and they were deeply impractical for submarines. A submarine's entire advantage is stealth. Surfacing to warn a merchant ship exposes the U-boat to gunfire, and the British quickly started arming merchant vessels and disguising warships as merchantmen, the infamous Q-ships. Surfacing to follow prize rules could get you killed. In February 1915, Germany declared the waters around the British Isles a war zone and announced that any vessel found in those waters could be sunk without warning. This was unrestricted submarine warfare, and it was a gamble with enormous political stakes. On May 7, 1915, the U-boat U-20, commanded by Captain Lieutenant Walter Schwieger, torpedoed the Cunard liner RMS Lusitania off the coast of Ireland. The ship sank in 18 minutes. 1,198 people died, including 128 Americans. The sinking provoked international outrage and became one of the factors that would eventually draw the United States into the war, though that wouldn't happen for another 2 years. Germany actually pulled back from unrestricted submarine warfare after the Lusitania for a while, under diplomatic pressure. But by early 1917, the military situation was desperate enough that they resumed it, calculating that they could starve Britain before America could mobilize. And for a while, the numbers were staggering. In April 1917 alone, U-boats sank over 860,000 tons of Allied shipping. Britain was losing ships faster than it could build them. Food supplies dwindled. The First Lord of the Admiralty, John Jellicoe, reportedly told American Admiral William Sims that the Allies were losing the war and that the submarine menace was the cause. Now think about this from an engineering perspective. These U-boats weren't particularly large or sophisticated by later standards. A typical German Type U-31 class boat was maybe 60 meters long, displaced around 970 tons submerged, had a crew of 35, carried 6 torpedo tubes, and could make about 16 knots on the surface and 9 submerged. Underwater endurance was limited, maybe 80 nautical miles at 5 knots on battery power before you had to surface and recharge. Dive depth was typically around 50 meters, maybe a bit more in an emergency. The hulls were riveted steel. The periscopes were simple optical tubes. The torpedoes were straight running, no guidance after launch. You aimed the whole submarine at the target, estimated the lead angle based on the target's speed and course, and fired. If your calculations were off, you missed. And the living conditions. You can imagine. 35 men in a steel tube 60 meters long and maybe 6 meters in diameter at the widest point. No shower. One toilet that couldn't be used below certain depths because the sea pressure would prevent flushing. Or worse, force the contents back up. The air grew foul within hours of diving. Condensation dripped from every surface. Food spoiled. Mold grew on everything. The diesel engines, even when shut down, left a pervasive smell of fuel oil that saturated clothing, hair, skin. Crew members developed skin rashes, respiratory problems, psychological strain. Patrols lasted weeks, and through all of this, you were being hunted. Because the Allies were learning to fight back. And the single most important tactical innovation wasn't a new weapon or a new technology. It was an old idea applied at scale: the convoy system. Instead of sending merchant ships across the Atlantic individually, where each one was a lone target, you grouped them together and escorted them with warships. The mathematics of it are counterintuitive but beautiful. A single ship sailing alone presents a certain probability of being spotted by a U-boat patrolling a given area. But a convoy of 30 ships doesn't present 30 times the probability of detection. It presents roughly the same probability as a single ship because the ocean is vast and the convoy occupies only slightly more visual space than one vessel. Meanwhile, the escorts, destroyers, armed trawlers, later aircraft, made attacking far more dangerous for the U-boat. The convoy system, once adopted in mid-1917, dramatically reduced losses. Sinkings dropped. The tonnage war swung back toward the Allies. But submarines had proven something that could never be unproven. A relatively small, relatively inexpensive fleet of underwater vessels had nearly brought the world's greatest naval power to its knees. The strategic calculus of naval warfare had changed permanently, and every navy in the world took notice because the interwar period, those 20 years between 1918 and 1939, became a time of intense submarine development. Bigger boats, better engines, longer range, deeper diving depths, more sophisticated torpedoes. The diesel-electric architecture remained the foundation, but everything around it was being refined, optimized, pushed further. And in Germany, despite the Treaty of Versailles explicitly forbidding them from building submarines, engineers kept working, quietly, through front companies in the Netherlands and Spain, through theoretical studies, through officer training programs disguised as other things, so that when Adolf Hitler repudiated the treaty restrictions in the 1930s, Germany didn't start from scratch. They had designs ready, experienced engineers standing by, and a strategic doctrine already developed for exactly the kind of tonnage war they'd nearly won the first time around. The man who would lead that effort was Karl Dönitz, a former U-boat commander himself, who had been captured by the British in 1918 and spent the interwar years thinking very carefully about what had gone wrong and how to do it better the next time. And Dönitz had answers. He'd studied every engagement, every patrol report, every tactical failure of the First World War U-boat campaign, and he'd arrived at a deceptively simple conclusion. The problem wasn't the submarines themselves. The problem was how they'd been used. In the First War, U-boats had mostly operated alone, individual hunters prowling shipping lanes, attacking targets of opportunity, then slipping away. And that had worked remarkably well for a while, but once the convoy system was adopted, a lone submarine suddenly faced a cluster of ships surrounded by armed escorts, and attacking became a much lonelier, much more dangerous proposition. One submarine against several destroyers isn't a fair fight. So Dönitz asked himself, what if the submarines didn't fight alone? His answer was the wolf pack, Rudeltaktik in German. The concept was elegant in its logic. Instead of scattering U-boats across the ocean to hunt individually, you'd spread them in a long patrol line across a likely convoy route. When one boat spotted a convoy, it wouldn't attack immediately. Instead, it would shadow the convoy and radio its position back to U-boat headquarters, back to Dönitz himself, sitting in an operations room with charts and pins and radio operators. Dönitz would then direct every available U-boat in the area to converge on that convoy. They'd gather like wolves around a herd, wait for nightfall, and then attack simultaneously from multiple directions. The escorts couldn't be everywhere at once. If 5 or 6 or 10 U-boats hit a convoy at the same time, from different angles, in the dark, the defenders were overwhelmed. They might chase one submarine and depth charge it, but while they were doing that, 3 others were firing torpedoes into the merchant ships from the opposite side. Think about what that means from a tactical standpoint. A convoy's greatest strength, concentrating the ships so you could concentrate the escorts, suddenly became a vulnerability, because Dönitz was concentrating his attackers too. He was matching the convoy's concentration with his own. And the coordination happened not through the submarines communicating with each other directly, but through centralized command. Everything flowed through Dönitz's headquarters. He was, in a sense, the conductor of an orchestra spread across thousands of miles of ocean. The U-boats were his instruments, and radio was the baton. Now, this reliance on radio communication would eventually become one of the Wolfpack's fatal weaknesses, but we'll get to that. First, let's talk about what happened when the Second World War began in September 1939, because Germany actually started the war with far fewer submarines than Dönitz wanted. He'd argued for 300 operational U-boats as the minimum needed to strangle Britain's supply lines. When war broke out, he had 57. Only about 26 of those were the larger Type 7 boats suitable for Atlantic operations. That's it. 26 submarines to take on the Royal Navy and cut off an island nation's lifeline. Dönitz was furious, but he worked with what he had, and even with those small numbers, the early results were devastating. The first phase of the Battle of the Atlantic, roughly from September 1939 through mid-1940, saw U-boats operating mostly individually, because there simply weren't enough of them to form proper wolf packs. But they still sank ships at an alarming rate. And then came what the U-boat crews themselves called Die glückliche Zeit, the happy time. After France fell in June 1940, Germany suddenly had access to French Atlantic ports: Brest, Lorient, Saint-Nazaire, La Rochelle, Bordeaux. This was transformative. Instead of having to sail all the way around the British Isles from German ports in the North Sea, U-boats could now operate directly from the French coast, cutting days off their transit time and dramatically extending the time they could spend on patrol in the shipping lanes. It was like moving your chess pieces several squares closer to the opponent's king in a single move. From roughly June 1940 through February 1941, a handful of U-boat aces, men like Otto Kretschmer, Günther Prien, Joachim Schepke, racked up staggering tonnage figures. Kretschmer alone sank 47 ships totaling over 274,000 tons during the war, making him the most successful submarine commander in history by tonnage. Prien had already become famous for sneaking into the Royal Navy's home anchorage at Scapa Flow in October 1939 and sinking the battleship HMS Royal Oak, a brazen attack that killed 833 sailors and shocked Britain to its core. These men were celebrities in Germany, their exploits splashed across newspapers and newsreels. But here's the thing about the happy time. It didn't last. All three of those aces were lost within days of each other in March 1941. Kretschmer was captured, Prien was killed when his U-47 was sunk, and Schepke died when a destroyer rammed his conning tower. The ocean was unforgiving, and the odds always caught up. But by then, the Wolfpack tactics were coming into full effect, and the real tonnage war, the one Dönitz had been planning for 20 years, was underway. And the numbers are staggering. In 1942, the worst year for the Allies, U-boats sank over 1,600 ships, totaling more than 7.7 million gross register tons. Think about what those numbers represent. Each of those ships carried food, fuel, ammunition, raw materials, vehicles, aircraft parts, everything Britain and eventually the broader Allied war effort needed to survive and fight. Every ship that went down took its cargo with it, and often its crew. Over the course of the entire Battle of the Atlantic, roughly 3,500 Allied merchant ships were sunk, along with 175 Allied warships. Around 72,000 Allied sailors and merchant mariners died. The human cost was enormous, and it played out not in dramatic single battles, but in thousands of individual encounters scattered across millions of square miles of cold, dark ocean, often at night, often in terrible weather. Now, let's talk about what it was actually like inside a U-boat during all of this, because the engineering constraints shaped every aspect of daily life in ways that are almost hard to believe. The Type 7, specifically the Type 7C, which was the workhorse of the German submarine fleet, was about 220 feet long and roughly 20 feet in beam. That's not a lot of space, and into that space you packed a crew of around 44 to 52 men. 4 torpedo tubes in the bow, 1 in the stern, a deck gun, diesel engines, electric motors, batteries, fuel tanks, fresh water tanks, food stores, ammunition, and all the mechanical and electrical systems needed to keep the thing running. There was essentially no personal space. Crew members shared bunks in a system called hot bunking. When one man got up for his watch, another man who'd just come off watch climbed into the same bunk, still warm from the previous occupant. The only private space on the entire boat was the captain's tiny curtained-off nook, and even that was barely large enough to lie down in. The air quality was a constant problem, and this connects right back to that fundamental engineering constraint we've been circling around since the very beginning of this story: the problem of breathing underwater. A submerged Type 7C had a limited supply of breathable air. Carbon dioxide built up. Humidity soared because there was no way to properly ventilate. The interior surfaces would drip with condensation. The smell was legendary, a combination of diesel fuel, unwashed bodies, bilge water, cooking grease, and the chemical tang of the battery compartment. Submariners couldn't shower. Fresh water was too precious for that. It was needed for the batteries and for drinking. After a few weeks on patrol, the crew's leather clothing would bloom with mold. Food stored in every available space would rot. The bread went stale, then green. And through all of this, these men had to maintain complex machinery, navigate by dead reckoning, stand watches, and go into combat. The engineering that made the Type 7 effective was a masterpiece of German precision manufacturing, but it was also a study in brutal compromise. The boat could make about 17 knots on the surface using its 2 supercharged diesel engines, and roughly 7 to 8 knots submerged on electric motors. But at maximum submerged speed, the batteries would drain in about an hour. At a more economical 4 knots, you could stretch that to maybe 80 hours, but that's still not very long. So the operational reality was that these boats spent most of their time on the surface, running on diesels, charging their batteries, and using their surface speed to get into position ahead of convoys. They only submerged to attack, to hide, or to avoid aircraft. The submarine of the Second World War was, in a very real sense, a surface vessel that could temporarily hide underwater, not a true underwater warship. This distinction matters enormously because it defined the tactical cat-and-mouse game of the entire Battle of the Atlantic. And here's where the technology race gets really fascinating, because both sides were innovating furiously, and each innovation triggered a counter-innovation in this escalating spiral that drove some of the most consequential engineering breakthroughs of the 20th century. Let's start with detection. How do you find a submarine? In the early war, the answer was mostly visual. Lookouts scanning the horizon for a periscope feather or a surfaced U-boat silhouette. Hydrophones could listen for propeller noise underwater, but they were crude and unreliable, especially in rough seas. What changed everything was radar. The British had been developing radar for air defense, but they quickly adapted it for naval use, and by 1941, escort vessels were being fitted with shipborne radar sets that could detect a surfaced U-boat at several miles range. This was devastating to the Wolfpack tactics, because remember, U-boats had to surface to move into attack position, to charge batteries, to communicate with headquarters. If they could be detected on the surface, the whole tactical framework started to crack. But the real game changer was airborne radar. When long-range patrol aircraft, Liberators, Sunderlands, Catalinas, started carrying radar sets that could spot a surfaced U-boat from miles away, the mid-Atlantic air gap began to close. That air gap, the stretch of ocean in the middle of the Atlantic that was beyond the range of land-based aircraft from either side, had been a safe haven for U-boats. They could surface there with relative impunity, recharge, communicate, reposition. Once very long-range aircraft with radar started covering that gap, starting in earnest in 1943, U-boats had nowhere to hide. And it gets more specific than that. The introduction of centimetric radar operating on a wavelength of about 10 centimeters, made possible by the cavity magnetron, a British invention so secret it was considered more valuable than the atomic bomb at the time. This centimetric radar was a quantum leap. Earlier metric wavelength radar sets emitted signals that the Germans could detect with their own radar warning receivers, giving U-boat crews time to crash dive before an aircraft arrived. But the new centimetric sets operated on a frequency the German receivers couldn't pick up. Suddenly, aircraft were appearing out of nowhere, catching U-boats on the surface with no warning. Submarines were being attacked and sunk before their crews even knew they'd been detected. And then there was the other secret, the one that arguably mattered even more than radar. The breaking of the Enigma cipher. The German military encrypted its communications using the Enigma machine, a device that generated codes of staggering complexity. Donitz's entire Wolfpack system depended on radio communication. Remember, he was coordinating everything centrally, radioing orders to boats spread across the Atlantic. Every one of those transmissions was encrypted with Enigma, and the Germans believed the code was unbreakable. They were wrong. At Bletchley Park, a sprawling estate in the English countryside, a team of mathematicians, linguists, and engineers, led in part by Alan Turing, one of the most brilliant minds of the 20th century, worked to crack Enigma. The effort was monumental, involving not just mathematical genius, but also the construction of electromechanical computing machines called bombs that could test thousands of possible key settings. The intelligence derived from breaking Enigma was codenamed Ultra, and it gave the Allies the ability to read German naval communications, sometimes within hours of transmission. They could see where the wolf packs were being directed, which patrol lines were being set up, which convoys were being targeted, and they could reroute convoys around the waiting U-boats, or vector escort groups directly to where the submarines were gathering. The impact of Ultra is still debated by historians. You can't cleanly separate its contribution from radar, from more escort vessels, from better tactics, from improved depth charges, and ahead-throwing weapons like Hedgehog. But the consensus is that it shortened the Battle of the Atlantic significantly, and by extension, shortened the entire war. The combination of all these factors came together in a terrible crescendo in May 1943, a month the Germans called Black May. In that single month, 43 U-boats were sunk. 43. Dönitz, who had been tracking losses with growing alarm, made a decision that effectively conceded the battle. He withdrew his U-boats from the North Atlantic. The wolf packs were pulled back. The tonnage war that Germany had been waging for nearly 4 years, the strategy Dönitz had been refining since his capture in 1918, had been defeated, not by a single weapon or a single breakthrough, but by an accumulation of technologies, tactics, and sheer industrial capacity that the U-boats simply couldn't overcome. But Dönitz didn't give up entirely. He kept hoping that new technology would swing the balance back. And this is where the story takes a turn that connects directly to the future of submarine engineering. because the Germans were working on something that would have changed everything if it had arrived sooner. It was called the Type 21, and to understand why it mattered so much, you have to remember that fundamental limitation we keep coming back to. The fact that a diesel-electric submarine was really a surface ship that could dive temporarily. The Type 21 was designed to flip that equation. It was meant to be a true submarine, a boat that could operate submerged for extended periods, that was faster underwater than on the surface, that could hunt and attack without ever needing to surface. And that idea, a submarine that lived beneath the waves rather than just visiting, was genuinely revolutionary. Everything that came before, from Holland's little boat puttering around New York Harbor to the wolf packs terrorizing the North Atlantic, all of those were vessels that spent most of their lives on the surface, breathing air, running diesel engines, and only ducked under when they had to. The Type 21 was supposed to change all of that. Here's what made it different. Start with the batteries. A conventional Type 7 carried something like 124 battery cells. The Type 21 carried roughly 3 times that, around 372 cells in some configurations. That's a massive increase in stored electrical energy, which translates directly into how long you can stay submerged and how fast you can go while you're down there. The Type 7C could manage maybe 4 knots submerged if it wanted to conserve battery, or about 7.5 knots in a sprint that would drain the batteries in roughly an hour. The Type 21 could do over 17 knots submerged. 17. That's faster than many escort vessels could manage, and it was faster than the boat's own surface speed on diesel. Think about what that means. For the first time, a submarine was actually better off staying underwater. The ocean itself became its advantage rather than its limitation. But batteries alone weren't the whole story. The hull design was completely rethought. Instead of the narrow, ship-like hull that most submarines inherited from their surface vessel ancestry, the Type 21 had a wider, more hydrodynamically streamlined hull optimized for moving through water rather than on top of it. The cross-section was almost figure-8 shaped, with the lower lobe housing those enormous battery banks and the upper section containing the crew spaces, torpedo rooms, and machinery. The whole thing was designed from the keel up to be an underwater vessel first and a surface vessel second. That might sound like an obvious approach, but it was genuinely radical in 1943. Every submarine navy in the world was still thinking of their boats as surface ships that could submerge. The Type 21 inverted that assumption. There was another innovation too, one that addressed the snorkel problem. Now, the snorkel, or schnorkel as the Germans called it, wasn't actually a German invention. The Dutch had developed the concept before the war, a retractable mast with a valve at the top that could be raised just above the surface, allowing the diesel engines to breathe while the submarine stayed at periscope depth. When the Germans captured the Netherlands in 1940, they found these devices and eventually started retrofitting them onto their existing U-boats in 1943 and 1944. The snorkel let a submarine run its diesels and charge its batteries without fully surfacing, which made it much harder for radar to detect. Instead of a whole submarine hull reflecting radar waves, you just had this small mast poking above the water. It wasn't perfect. The head valve would sometimes slam shut in heavy seas, and when it did, the running diesels would suddenly start sucking air from inside the submarine, which could cause painful and dangerous pressure drops that left crews with burst eardrums and bleeding noses. But it worked well enough to dramatically improve survivability against radar-equipped aircraft. The Type 21 was designed with the snorkel integrated from the start, not bolted on as an afterthought. Combined with those massive battery banks and that streamlined hull, it could transit to its patrol area snorkeling, arrive on station, then operate entirely on battery for days at a time, creeping at low speed or sprinting to attack. It also carried a sophisticated new sonar system that allowed it to fire torpedoes from depth using sonar data alone without ever raising a periscope. That's another quiet revolution. The idea that you could detect, track, and engage a target without ever looking at it with your eyes. Now here's the thing that makes the Type 21 one of those great what-if stories of the war. It came too late. Albert Speer, Hitler's armaments minister, pushed for an ambitious production plan using prefabricated sections built at inland factories and then transported to shipyards for final assembly. An approach borrowed from the modular construction techniques that Henry Kaiser was using to build Liberty ships in America. The idea was to mass-produce these boats quickly, churning out dozens per month. And on paper, the plan was impressive. Over 100 Type 21s were technically completed by the end of the war. But Allied bombing had devastated German industry and transportation networks. The prefabricated sections often didn't fit together properly because different factories were working under chaotic conditions with degraded quality control. Training crews took time that Germany didn't have. Of all those boats completed, only a handful ever went on operational patrols, and only one, U-2511, commanded by Kapitänleutnant Adalbert Schnee, actually conducted something close to a combat patrol. Even then, the war ended before Schnee could press home an attack. He reportedly made a simulated torpedo run on a British cruiser on the last day of the war, proving the boat could get into attack position undetected, then surfaced to surrender. So the Type 21 never changed the outcome of the war, but it absolutely changed the future of submarine design. When the Allies captured these boats and studied them, they recognized immediately that this was the shape of things to come. The Americans launched a program called Guppy, Greater Underwater Propulsive Power, that essentially rebuilt their existing fleet submarines along Type 21 principles: streamlined hulls, snorkels, enlarged battery capacity, removal of deck guns and other surface warfare equipment that created drag underwater. The Soviets did the same thing with captured Type 21s, and the British studied them closely too. For about a decade after the war, every major submarine navy in the world was essentially iterating on what the Germans had started with the Type 21. But even the Type 21, for all its advances, was still fundamentally limited by the same constraint that had dogged submarines since the very beginning. It still needed air. The diesels needed air to burn fuel. The batteries, no matter how many you packed in, eventually ran down and needed recharging, which meant running the diesels, which meant either surfacing or snorkeling. The snorkel helped enormously, but it still tethered the submarine to the surface in a way. A snorkeling submarine is detectable by radar, by visual lookout, by the wake the mast creates. The dream of a submarine that could stay submerged indefinitely, that never needed to interact with the surface at all, that was still out of reach. And this is where the story shifts from wartime desperation to something more like pure engineering ambition, because in the years right after the war, a small number of people started thinking seriously about what it would take to cut that last tether to the surface. What if you could build a power source that didn't need air at all? What if the engine could run in a completely sealed environment, submerged at depth, for weeks or months at a time? There had been attempts at this before. The Germans themselves had experimented during the war with a system called the Walter turbine, designed by Helmuth Walter, an engineer who'd been working on hydrogen peroxide propulsion since the 1930s. The concept was clever. You take highly concentrated hydrogen peroxide, decompose it using a catalyst, and the reaction produces steam and oxygen. You can then inject fuel into that oxygen-rich steam, burn it in a combustion chamber, and use the resulting high-pressure gas to drive a turbine. No atmospheric air needed. The whole cycle is closed, or nearly so. Walter built experimental boats, the Type 17, and they were startlingly fast underwater, capable of over 25 knots submerged. But hydrogen peroxide is terrifyingly dangerous stuff. Concentrated to the levels Walter needed, around 80 to 85%, it's a powerful oxidizer that can decompose explosively if it contacts the wrong material. A speck of rust, a bit of organic contamination, and you can get a violent reaction. The British experimented with Walter-type propulsion after the war in a submarine called HMS Explorer, which the crews nicknamed HMS Exploder, for reasons that probably don't need much explanation. The Soviets also tried hydrogen peroxide systems with similarly alarming results. The technology worked in principle but was just too dangerous for practical fleet use. So hydrogen peroxide wasn't the answer. But something else was emerging from a completely different branch of science, something that had nothing to do with submarine engineering at all until one man made the connection. And that man was Hyman G. Rickover. Now, Rickover is one of those figures in engineering history who you almost can't believe was real. He was difficult, abrasive, politically cunning, technically brilliant, and absolutely relentless. He was born in 1900 in what's now Poland, came to the United States as a child, grew up in Chicago, and entered the Naval Academy at Annapolis. He wasn't popular there. He was small, bookish, Jewish, in an institution that wasn't particularly welcoming to Jewish officers, and he had a personality that could charitably be described as prickly. He served on surface ships and then transferred to submarines in the 1930s, eventually commanding an old S-boat. But it was his engineering mind that set him apart, and after the war, in 1946, he was sent to Oak Ridge, Tennessee, as part of a small group of naval officers assigned to learn about nuclear energy. And this is where Rickover saw something that almost nobody else in the Navy was seeing yet. He looked at nuclear fission, this process where splitting uranium atoms releases enormous amounts of energy. And he didn't think about bombs. He thought about steam. He thought about a reactor that could heat water, produce steam, drive a turbine, turn a propeller, and do all of it in a sealed system that consumed no oxygen and produced no exhaust. A submarine with a nuclear reactor wouldn't need to surface, ever. It wouldn't need to snorkel. It wouldn't need diesel fuel. It could stay submerged at high speed for as long as the crew could endure and the food held out. The limiting factor would no longer be the machine. It would be the human beings inside it. That vision was clear to Rickover almost immediately, but turning it into reality would take nearly a decade of political maneuvering, engineering breakthroughs, and the kind of stubborn, bulldozing determination that made Rickover both legendary and deeply unpopular within the Navy's own bureaucracy. Because the Navy didn't particularly want a nuclear submarine in 1946. The admirals were focused on carriers and surface fleets. Submarines were still seen by many as a secondary arm, useful but not prestigious. And nuclear technology was exotic, expensive, and controlled by the newly formed Atomic Energy Commission, which meant the Navy couldn't just build what it wanted. It needed civilian approval and cooperation. Rickover positioned himself at the intersection of these two worlds, holding positions in both the Navy's Bureau of Ships and the AEC simultaneously, answering to both and using each against the other when it suited him. He handpicked his team, personally interviewed every officer who would serve in the nuclear program, interviews that became legendary for their intensity and psychological pressure. And he drove his engineers with a perfectionism that bordered on obsession. Engineers who worked under Rickover described an atmosphere where a 99% solution was treated as a failure. He wanted to know every weld, every valve, every pipe fitting. He wanted to understand the metallurgy of every component that would sit inside a reactor compartment. And the reason for that intensity wasn't ego. Or at least, it wasn't only ego. It was the simple, terrifying math of what they were attempting. They were going to put a nuclear reactor inside a steel tube, submerge it hundreds of feet below the ocean surface, fill that tube with over 100 human beings, and send it out to sea for months at a time. There was no margin for error. A reactor malfunction on land is a disaster. A reactor malfunction 300 feet underwater, inside a pressure hull, with nowhere to evacuate, that's something else entirely. Rickover understood this in his bones, and it shaped everything about how the program was built. The engineering challenge was staggering. Nobody had ever built a compact nuclear reactor that could fit inside a submarine hull. The reactors at Oak Ridge and Hanford were enormous industrial facilities sprawling across acres of land. What Rickover needed was a reactor small enough to fit in a compartment maybe 30 feet long, powerful enough to drive a submarine at over 20 knots submerged, safe enough to operate with a crew sleeping on the other side of a bulkhead, and reliable enough to run for years without major maintenance. Every single one of those requirements was, in 1947, somewhere between extremely difficult and technically impossible. He started by choosing the reactor type. There were several competing concepts: sodium-cooled reactors, gas-cooled reactors, various exotic designs. Rickover, working with the team at Argonne National Laboratory and later with Westinghouse, settled on a pressurized water reactor, or PWR. And here's why that choice was so clever. In a pressurized water reactor, you use ordinary water, plain old H2O, as both the coolant and the moderator. The moderator is the substance that slows down the neutrons flying out of the fissioning uranium, so they're more likely to hit other uranium atoms and keep the chain reaction going. Fast neutrons tend to zip right past uranium-235 without interacting. Slow them down, and the probability of fission goes way up. Water happens to be excellent at this, so the water circulates through the reactor core, absorbs heat from the fission process, and simultaneously keeps the chain reaction regulated. Here's the beautiful part. And this is one of those elegant engineering features that makes you appreciate how thoughtful the design was. If the reactor starts to overheat, the water gets hotter. When water gets hotter, it becomes less dense. When it becomes less dense, it's less effective as a moderator. Fewer neutrons get slowed down. Fewer fissions occur. The reactor automatically throttles itself back. It has a built-in negative feedback loop. The physics itself acts as a safety mechanism. That's not something you bolted on as an afterthought. It's intrinsic to the design. Now, the pressurized part of pressurized water reactor is important too. Under normal atmospheric pressure, water boils at 100 degrees Celsius, 212 Fahrenheit. But Rickover's reactor needed water much hotter than that to efficiently transfer heat and generate steam. So the primary cooling loop, the water that actually flows through the reactor core, is kept under enormous pressure, something like 2,000 pounds per square inch. At that pressure, water stays liquid even at temperatures well above 300 degrees Celsius. This superheated, high-pressure water then flows through a heat exchanger, a steam generator, where it transfers its thermal energy to a secondary loop of water that's at lower pressure. That secondary water boils into steam, and that steam drives the turbines that turn the propeller shaft and also power the electrical generators for everything else on the boat. The key thing is that the radioactive water in the primary loop never directly contacts the steam that drives the turbines. Two separate loops. The radioactivity stays contained within the reactor compartment, behind heavy shielding, and the rest of the submarine operates with clean, non-radioactive steam. Think about that design for a second. It's essentially a very sophisticated way of boiling water, which when you strip away all the nuclear physics, is exactly what it is. Rickover himself reportedly said something to the effect that a naval reactor is just a complicated way to boil water. He wasn't wrong, but making it work in practice was a nightmare of materials science. The inside of a reactor core is one of the most hostile environments you can engineer for. You've got intense radiation bombarding every surface. You've got water at extreme temperature and pressure. You've got vibration from the machinery and from the sea itself, and everything has to function flawlessly for years. Radiation does terrible things to metals over time. It makes them brittle, changes their crystalline structure, causes them to swell or crack. Finding alloys that could withstand this environment, fabricating them to exacting tolerances, developing welding techniques that produce joints strong enough to contain 2,000 pounds per square inch of radioactive water. Every one of these was a research project in itself. Rickover drove Westinghouse and their subcontractors relentlessly. He stationed his own inspectors in the factories. He rejected components that didn't meet his standards, even when it meant delays of months. There are stories of him personally reviewing the qualification records of individual welders. That level of micromanagement would be pathological in most contexts, but in this context, where a single bad weld could mean a reactor breach inside a submerged submarine, it was arguably the only sane approach. The first major milestone came not at sea, but in the Idaho desert. Rickover insisted on building a full-scale prototype reactor, designated S-1W, inside a complete mock-up of a submarine hull, built on land at the National Reactor Testing Station in Arco, Idaho. The whole thing was constructed inside a massive metal tank that could be filled with water to simulate ocean pressure. This was Rickover being Rickover. He didn't want to test the reactor in some abstract laboratory setting. He wanted to test it in conditions as close to real submarine operation as possible, so that when they finally put a reactor in an actual submarine, they'd already know it worked. The prototype reached criticality, meaning the chain reaction became self-sustaining, on March 30th, 1953. And then they ran it. They ran it hard, simulating a full-speed transatlantic crossing without surfacing, pushing the reactor through every operating condition they could imagine. It worked. It worked beautifully. Meanwhile, the submarine itself was being built at the Electric Boat Shipyard in Groton, Connecticut, the same yard that had built submarines for the Navy going back decades. The hull was designated SSN 571, and the boat was named Nautilus, a deliberate echo of both Jules Verne's fictional submarine and Robert Fulton's real one from a century and a half earlier. The Nautilus was launched on January 21st, 1954, with First Lady Mamie Eisenhower breaking the traditional bottle of champagne across her bow. And on January 17, 1955, the Nautilus put to sea under nuclear power for the first time, sending the now famous signal, "Underway on nuclear power." And here's where you really feel the magnitude of what had changed. On her early trials, the Nautilus submerged and just kept going. She traveled 1,381 miles from New London, Connecticut to San Juan, Puerto Rico, completely submerged in less than 90 hours. That's an average speed of over 15 knots underwater the entire way. No submarine in history had done anything remotely like this. The best diesel-electric boats could maybe manage a few dozen miles submerged at moderate speed before their batteries were exhausted. The Nautilus covered over 1,000 miles without surfacing and could have kept going indefinitely. The ocean had fundamentally changed. A submarine was no longer a surface ship that could hide underwater for a little while. It was a true underwater vessel that never needed to surface at all. Think about what that meant tactically. Every anti-submarine technique that had been developed in 2 world wars, the convoy system, the patrol aircraft, the radar searches for snorkels and periscopes, the hunting groups that waited for U-boats to surface and recharge, all of it became largely irrelevant overnight. A nuclear submarine didn't surface. It didn't snorkel. It didn't need to come to periscope depth to run its diesels. It could operate at depths and speeds that made it incredibly difficult to detect, track, or attack. The entire calculus of naval warfare shifted. But Nautilus, for all her revolutionary propulsion, was still essentially a traditional submarine shape. She had the same kind of hull form that submarines had used for decades, optimized partly for surface running. And that's where the story takes another turn, because even as Rickover was perfecting the nuclear reactor, another group of engineers was rethinking the hull itself. The man at the center of this was a naval architect and hydrodynamicist whose work would prove just as transformative as Rickover's reactor, though he's far less famous. His name was Harry Jackson, and he was working at the David Taylor Model Basin, the Navy's premier facility for testing ship designs. But the real conceptual breakthrough had been championed a few years earlier, and it resulted in a strange little experimental submarine that looked nothing like any submarine before it, a vessel that would change the shape of every submarine built afterward. She was called the USS Albacore, and what made her special wasn't what was inside her, but what was outside. Her hull. The shape of her body moving through the water. See, every submarine up to that point, every single one from Holland's little cigar-shaped boat in 1900 all the way through the fleet boats of World War II, and even Nautilus herself, had been designed with a compromise baked in. They had to work on the surface and underwater. And those are 2 very different problems. A good surface hull is long, narrow, with a sharp bow that cuts through waves. A good underwater hull is something else entirely. Water is about 800 times denser than air, so when you're fully submerged, the dominant force you're fighting isn't wave resistance. It's drag. Friction drag from the water sliding along your skin, and form drag from the shape of your body, pushing water out of the way. And the ideal shape for minimizing drag underwater isn't a long, sleek surface ship. It's something rounder, fatter, more like a teardrop, or if you want the technical term, a body of revolution, a shape that's circular in cross-section, widest about 1/3 of the way back from the nose, then tapering smoothly to a point at the tail. This was actually well-understood physics. Aerodynamicists and hydrodynamicists had known for decades that a teardrop shape had the lowest drag coefficient of any simple form moving through a fluid. The problem was that nobody had been willing to build a submarine that looked like that, because a fat teardrop is terrible on the surface. It wallows, it rolls, it's slow and uncomfortable in waves. And since submarines spent most of their time on the surface, or at least had to transit on the surface regularly, you couldn't just throw away surface performance. Until nuclear power came along and said, actually, maybe you can. The Albacore project started in the late 1940s, before Nautilus was even under construction. The idea came from a group of researchers and engineers who argued that the Navy needed a pure hydrodynamic test platform, a submarine designed exclusively for underwater performance, with no compromises for surface operation. Harry Jackson, was instrumental in the design work, running endless tests in the towing tanks at the David Taylor Model Basin, dragging scale models through water and measuring the forces. And what he and his colleagues found confirmed what the theory predicted. A teardrop hull with the right proportions could achieve dramatically lower drag than a conventional submarine hull. We're talking about reductions of 60% or more at the same speed. Or, to flip it around, the same power plant could push a teardrop hull much, much faster underwater. USS Albacore was commissioned in December 1953, just a month before Nautilus launched. She was small, about 204 feet long, with a crew of around 52. And she was diesel-electric, not nuclear. She wasn't meant to be a combat submarine. She was a floating laboratory. And she looked absolutely bizarre compared to anything the Navy had built before. No deck gun, no sharp bow, no traditional conning tower. Just this smooth, rounded body with a single propeller at the back and a small, streamlined sail. That's the fin-like structure on top where the periscopes and masts are housed. She looked more like a blimp or a fat torpedo than a warship. And she was fast. During her trials, Albacore reached submerged speeds that were, for the time, astonishing. Over 33 knots in some configurations. That's faster than most surface warships. On a diesel-electric plant, the hull shape was doing that much work, reducing drag so dramatically that even modest power could produce remarkable speed. The Navy ran her through multiple phases of modifications over the years, testing different control surfaces, different bow shapes, dive brakes, even different propeller configurations. She was basically a full-scale wind tunnel for underwater design. And everything they learned went straight into the next generation of submarines. Here's the thing that makes this story so elegant. You had two parallel revolutions happening at almost exactly the same time. Rickover was solving the endurance problem, giving submarines unlimited power and air. Jackson and the Albacore team were solving the hydrodynamic problem, giving submarines the ideal shape for moving through water efficiently. And when you combined those two breakthroughs, you got something that was genuinely new in the history of naval warfare. You got the Skipjack class. USS Skipjack, commissioned in 1959, was the first operational submarine to marry a nuclear reactor with an Albacore-style teardrop hull. And she was a revelation. Skipjack could sustain over 30 knots submerged indefinitely. Not for a few minutes on battery, not in a desperate sprint, continuously, for as long as the crew could endure. She was faster underwater than most of the surface ships trying to hunt her. She could dive deep, maneuver aggressively, and stay down forever. If Nautilus had made the old anti-submarine warfare playbook obsolete, Skipjack tore it up and burned the pieces. This was the template. Every American submarine built after Skipjack, every single one, from the attack boats to the ballistic missile submarines, used some version of this combination: nuclear propulsion, teardrop-derived hull form. And not just American submarines. The Soviets adopted similar hull shapes. The British, the French, the Chinese. Everyone converged on the same basic answer, because the physics didn't care about your nationality. A teardrop is a teardrop. Drag is drag. And this brings us to the other enormous chapter in submarine history that was unfolding simultaneously: the ballistic missile submarine. Because right around the time Skipjack was proving what a fast nuclear attack boat could do, another group of engineers was working on something even more consequential. They were figuring out how to put nuclear missiles inside a submarine. And this wasn't just a military innovation. This was arguably the single most important strategic development of the entire Cold War, because it created the concept of the survivable second strike. Let me explain what that means, because it matters. By the late 1950s, both the United States and the Soviet Union had nuclear arsenals large enough to destroy each other many times over. The terrifying problem was stability. If one side believed it could launch a surprise first strike and destroy all of the other side's nuclear weapons before they could be used, then in a crisis, there was a powerful incentive to strike first. Use them or lose them. That's an incredibly dangerous dynamic. What you needed for stability was a guarantee that even after absorbing a full-scale nuclear attack, you could still retaliate with devastating force. If both sides had that guarantee, then neither side had any incentive to strike first, because they knew retaliation was assured. This is the logic of deterrence, and it only works if your retaliatory weapons can survive the first strike. Land-based missiles in fixed silos are vulnerable. Bombers on runways are vulnerable. But a submarine? A submarine hiding somewhere in the vast, deep ocean, silent, undetectable, carrying 16 or 24 nuclear missiles that can reach any target on the continent? That submarine is essentially invulnerable. You can't find it. You can't target it. You can't destroy it preemptively. And as long as it exists out there, somewhere, the other side knows that launching a first strike would be suicide because the retaliation would come from beneath the sea. The first American ballistic missile submarine was USS George Washington, commissioned in December 1959. She carried 16 Polaris A-1 missiles, each with a nuclear warhead, each with a range of about 1,200 nautical miles. She was based on a skipjack hull that was literally cut in half during construction and had a 130-foot missile section inserted. On July 20th, 1960, George Washington successfully launched 2 Polaris missiles while submerged, the first submarine-launched ballistic missile firings in history. Her commanding officer sent a message back to shore that read, simply, "Polaris, from out of the deep to target. Perfect." And with that, the world changed again. The Soviets developed their own ballistic missile submarines. The British built theirs. The French built theirs. And for decades now, these submarines have been quietly patrolling the deep oceans, undetected, carrying enough destructive power to end civilization, and in doing so, paradoxically, helping to prevent the very war they were built to fight. It's one of the strangest and most sobering facts of modern life. Right now, tonight, as you're lying here listening to this, there are ballistic missile submarines on patrol in the Atlantic and the Pacific, and probably under the Arctic ice cap. American Ohio-class boats, each carrying 20 Trident II missiles, each missile carrying multiple independently targeted warheads. British Vanguard-class boats, Russian Borei-class boats, French Triomphant-class boats. They're out there right now, in the dark, in the deep, crewed by men and women who spend months at a time in a steel tube, maintaining the machinery of deterrence. And almost nobody thinks about them. So let's think about what's actually happening inside one of those modern submarines, because the engineering has come an extraordinary distance from Drebel's leather-wrapped rowboat in the Thames. A modern nuclear submarine is essentially a self-contained world. The reactor provides virtually unlimited electrical power and propulsion. That electricity runs everything: the lights, the computers, the sonar systems, the weapons systems, the galley where the cooks make meals for a crew of over 100. It powers the oxygen generators, which use electrolysis to split seawater into hydrogen and oxygen, giving the crew fresh air indefinitely. It powers the carbon dioxide scrubbers that pull CO2 out of the atmosphere and keep it breathable. It powers the desalination systems that turn seawater into fresh, drinking water. The only real limit on how long a modern nuclear submarine can stay submerged is food. They carry enough provisions for roughly 90 days, and that's typically what determines patrol length. Not fuel, not air, not water. Food. That would have been unimaginable to the men who crewed the Hunley, hand-cranking through Charleston Harbor with a candle for light and whatever air happened to be trapped inside. And the quieting. We should talk about the quieting, because in modern submarine warfare, silence is everything. The primary way you detect a submarine is by listening for it. Passive sonar, essentially very sensitive, underwater microphones called hydrophones, often towed in long arrays behind surface ships or other submarines, or mounted on the ocean floor. And the engineering effort that has gone into making submarines quiet is staggering. Every piece of rotating machinery inside a modern submarine is mounted on vibration-isolating rafts. The propulsion systems use natural circulation reactor designs that can operate without running the primary coolant pumps at low speeds, eliminating a major noise source. The propellers, or more accurately, the pump jet propulsors used on the latest boats, are designed with geometries so carefully optimized that they delay the onset of cavitation, which is the formation and collapse of tiny vapor bubbles that creates noise. The hull itself is coated in anechoic tiles, rubbery, sound-absorbing material that reduces the echo returned by active sonar pings and dampens internally generated noise. The entire engineering philosophy is organized around one principle: be quieter than the ocean itself. And that's really the ultimate expression of everything we've been talking about tonight, isn't it? From the very beginning, the submarine has been about hiding, about using the ocean as a cloak. Drebel figured out you could go under the surface. Bushnell figured out you could use that to attack a warship. Holland figured out how to make it practical. The diesel-electric boats of the world wars figured out how to make it lethal on a massive scale. Rickover figured out how to stay under forever. Jackson figured out the right shape to move through the deep efficiently. And generation after generation of engineers have figured out how to make these machines quieter, deeper diving, more capable, more autonomous. Every single one of those steps came down to someone, usually a lot of someone's, solving a specific, concrete engineering problem. How do you keep water out? How do you keep air in? How do you see without being seen? How do you generate power without consuming the air your crew needs to breathe? How do you build a steel cylinder that can withstand the crushing pressure at 1,000 feet? How do you contain a nuclear reactor inside a vessel that has to be absolutely silent? Each of those questions has an answer, and each answer is a story of materials and mathematics and testing and failure and trying again. And maybe that's the thing to hold on to as you drift off tonight. Somewhere out there, right now, beneath the surface of an ocean you might never visit, there's a machine that represents centuries of accumulated human ingenuity. It's gliding through water that's barely above freezing, at a depth where sunlight never reaches, in perfect silence. Inside, someone is standing watch, monitoring the reactor, checking the depth gauge, listening to the ocean on sonar. The coffee is probably terrible. The bunks are narrow. The air smells faintly of amine from the CO2 scrubbers. But the engineering works. The hull holds. The reactor hums. The oxygen flows. And the ocean, vast and dark and patient, keeps its secrets, just as it always has. The submarine simply learned how to become one of them.